Login accepted.
All right, hi everyone. My name is Andrew, and today I'm going to be giving a talk titled Memory Safety and the Future of Vulnerabilities. So, first thing is just who I am. So I'm a principal engineer for MITRE. I'm not here representing MITRE today, but basically just for people who are unfamiliar with MITRE. MITRE is a not-for-profit that operates federally funded research and development centers, which is a long name that basically means that MITRE does research and development for different parts of the US federal government. I've also been a Rustation for 11 years, which is the name for people who write Rust code, program in the Rust programming language. So today is going to touch a bit on Rust and kind of the topic of memory safety, so that's why I'm bringing that up. Before I get into the rest of the talk, I will also just make a plug for, so this last week I was at VulnCon, which is a conference on the vulnerability management ecosystem. It's really populated by people who are involved with CVE, which is the largest system for tracking known vulnerabilities, as well as NVD, which is the National Vulnerability Database. It was a really great, interesting conference. They encourage student participation. The next two will be in Arizona. They haven't published the full information for them yet, but if anyone is interested in vulnerability management, it's a conference to look out for next year that I think is would be really useful to attend. So all that said, what is memory safety? Topic that gets thrown around a lot. If you've looked at Rust at all, it's like the major thing that people will promote about the Rust programming language is that it is a memory safe programming language. Not that it's the only benefit of Rust, but it's the most sort of interesting or exciting thing about Rust. Informally, memory safety is when programs cannot produce certain types of software weaknesses related to the use of memory. Now, what kinds of weaknesses? This is a definition from Michael Hicks, who's a programming language researcher and professor. This is kind of like a nice short version. He identifies a few things. Buffer overflow, the classic one, null pointer dereferences, use after free, use of uninitialized memory, and illegal free. So this would be like double free is what you commonly see it called, or trying to free a pointer that wasn't allocated from the heap. All of this is to say, these are all things related to misuse of memory in some way, where you are accessing memory which hasn't properly initialized, you're trying to free memory which shouldn't be freed, you're going past the end of some memory that's been allocated to you by the system allocator. And in any of those cases, you're basically sort of violating what should be a core constraint, which is that you should only be able to access the memory that is allotted to you. And obviously that can be very bad when you are violating those kinds of things. Another way to think about it is that people will sometimes split these into temporal versus spatial memory safety, and we'll get into that a little bit more in a minute. There is also this bigger list. So there's this taxonomy called the Common Weakness Enumeration, or CWE. It's a thing actually that MITRE, the company I work at, maintains, and it is a very detailed breakdown of the kinds of weaknesses that can occur in software. And when I say weakness, that has a specific technical definition, which is essentially that these are bugs in software that are not necessarily exploitable vulnerabilities, but that are the precursor to having an exploitable vulnerability. So any actual CVE, any actual vulnerability that is found out in the wild is going to have some associated software weakness associated with it. And so this is just the giant taxonomy of those weaknesses. And they have a category for memory safety. It is very detailed. So like buffer overflow that it was on the last page becomes like 5 different CVE entries, depending on the specific flavor of buffer overflow that you're talking about. It's great, it's very useful. You can be very precise about what kind of weakness you're describing, but I think often just saying buffer overflow is more excessive. So know that this list exists, and you can go look at it if you'd like. It's informative, but usually we'll just say things like buffer overflow or null pointer dereference. Now, I mentioned also that you can split these types of vulnerabilities into categories. So spatial memory safety is the first one. Basically, out of bounds accesses, buffer overflows. Joshua Weitz, who's a person in the Rust programming language community, has a nice blog post that kind of breaks down the difference between spatial and temporal memory safety. You can sort of, within a buffer overflow, talk about whether it's that you are reading or writing outside of the bounds of a buffer, or if you're going over or under, so sort of which side of the buffer you are going past. But at any rate, when we're talking about spatial memory safety, that's what we're talking about. Who here has heard of Heartbleed? Hey, awesome. Okay, so Heartbleed was a vulnerability in OpenSSL reported in 2014 that was a spatial memory safety vulnerability and was very bad, extremely consequential, very expensive to deal with. The basic idea with Heartbleed was that there was a feature which had been added to TLS, the underlying specification being implemented, that basically said that you could check that a connection is still alive by sending a heartbeat message to a server. So a client would say, send some text, and then basically get that text echoed back to them by the server. And the problem with Heartbleed was that you could, as the client, lie about how large your message was, and it would just sort of be accepted. So you could say hello, and normally you'd say that that's 6 characters because it's the 5 for hello plus a null terminator because we're talking about C. But instead, you could say like hello, and oh, by the way, this was like 10,000 characters long. And the server would say, oh, awesome. Okay, well, I'll echo back hello, and everything else after that in memory that I haven't initialized based on the size of buffer you told me to allocate. So the end result of that was that whatever happened to be resident in memory in that extra stuff that was in that buffer would just get returned to the client. And that could be literally anything that was at some point in memory on the target. That could be sensitive key material, it could be passwords, it could be other sensitive data. You're sort of bypassing all of the access controls by just getting access to whatever happens to be there in memory. Extremely bad, and that's kind of the worst case of what we're talking about when we're talking spatial memory safety issues. Oh yeah, and I guess I had a little breakdown of what you could do, and you can imagine it's got like a social security number in it and other stuff that just happens to be sitting in memory. There's also, now this is an older article, you may not have heard of it, Smashing the Stack for Fun and Profit. Who here has ever heard of this one? I'm impressed that anyone has heard of this. This is from the late 90s. But basically, this was like the first major article where someone really broke down how to turn buffer overflows into remote code execution. It's a classic. A lot of the details, like the fundamentals of what it's describing is all pretty much still true, with the caveat that systems have gotten better at instituting defenses to make the specific techniques that this describes no longer work. But the basic ideas of like how you turn a buffer overflow into remote code execution is still there. And this is still a very fun article to read. And so this is a stack-based buffer overflow into a remote code execution. Another example of why we care about this kind of memory safety. Now, with temporal memory safety, so things like use after free, use of uninitialized memory, double free, these are basically, so with use after free and uninitialized memory, the issue is that you're doing operations on memory that could have arbitrary junk. So if you have a pointer to some piece of memory and you have freed that memory, that means you have given it back to the allocator and said like, hey, I'm done with this, you can give it to another program. That could very well happen. But if you are keeping that pointer around and then try to read to that piece of memory, you might access data that isn't intended for you to access that's now being written to by another program. Now, you could also get what's called a segmentation fault. This is basically what happens when you have tripped up the underlying protections around writing or accessing memory that's in a different page than you're supposed to have access to. A segmentation fault is the best case scenario in this, because with a segmentation fault, your program dies. Without a segmentation fault, you end up either accessing garbage, you might have like arbitrary, ridiculous program behavior because you're now completely off the rails operating on completely unexpected data. You have unintended disclosure of sensitive data. All of these things are problematic. And then with double free, allocators get very angry when you try to free a pointer that you've already freed. The specific behavior is going to depend on the allocator that you're dealing with, but none of the answers for what happens on a double free are. Again, best case, your program gets killed, but not best case, it exhibits arbitrary bad behavior that is very difficult to debug. So all of that to say, memory safety is when that doesn't happen. Basically when you can guarantee with your program, either at compile time or runtime, that all of those different types of weaknesses that I just described do not happen. And when we talk about memory safe languages, these are languages that stop memory safety problems. Now, I'll add a caveat here, which is that people will sometimes point out, for example, with Rust. So Rust is a memory safe programming language, but it has the ability to do unsafe operations. This basically says that when you have written unsafe Rust code, you get some extra powers to let you do things that the compiler cannot validate are safe, and you sort of take the safety into your own hands and are responsible for enforcing it. And so another way to think of this when we talk about memory safe languages versus memory unsafe languages is that memory safe languages are memory safe by default, and you have to opt into not getting the safety guarantees, versus languages like C or C++, which are memory unsafe by default. So what languages are memory safe? This is a table that I copied from a paper called The Case for Memory Safe Roadmaps. This is a lot of acronyms, but this is basically all of the different agencies in the US and the other Five Eyes countries. So that's Canada, the UK, Australia, and New Zealand, that basically all collaborated on this paper to recommend that organizations try to plan for transitioning to memory safe language. At the end, in an appendix, they have this table that identifies some memory safe languages. This is not an exhaustive list, but this is kind of like the popular languages that you might imagine are memory safe. So it's got Rust in there, but it's also got things like C#. Yeah, it's got Java, Go. So Rust doesn't have a monopoly on memory safety. Rust innovation is that it's a memory safe language that enforces memory safe compile time rather than at runtime. But all of these other languages are still also memory safe, with the one caveat being that some of them are memory safe, but they do permit what's called a null pointer dereference. This is basically where you are trying to access data that's at a pointer that's null, it's pointing to 0 address, which is generally just treated as invalid. Usually when you do that, you're going to get like a segmentation fault or other kind of program. Some of these will permit that. So like you can have segmentation faults and null pointer dereference issues in Go, you can have them in Java. It's a thing to be aware of, but it's less concerning than some of the other things. Outcome from that generally going to be like a denial of service or an availability loss rather than like heartbleed, like arbitrary loss of data or like a remote code execution. So which languages aren't memory safe? Pretty much we're talking about C and C++. There are others, they're not nearly as popular. These are like the two big ones, and they're holdouts. And they've historically been used in areas where you had really tight resource constraints or really strong performance requirements that made it difficult to accept the performance penalty of garbage collection. Because for a long time, the mechanism we had for enforcing memory safety was garbage collection. It requires that there is a garbage collector running alongside your program, and either concurrently or with periodic stopping and starting, collecting garbage data when it's no longer used by your program. So because you had that sort of constraint that you couldn't accept garbage collection, it's like, okay, well, I'm going to use C and C++, and I'm taking the safety into my own hands. And so then Rust arrived, that's the Rust logo, and suddenly became a memory safe option for this context. Rust 1.0 was May 15th, 2015. Personal trivia, also the day of my first date with my wife, which makes that release date very easy to remember. But yeah, Rust basically is the first memory safe language to really be usable in that context of kind of resource constrained or very performance sensitive. You have like embedded contexts, all these places where you would use C or C++ previously. Rust was suddenly a viable option that afforded memory safety. So then 9 years later, the White House publishes this. And so when I say the White House, so if you can't read it, it's Future Software Should Be Memory Safe. This is specifically the Office of the National Cyber Director, which is a cybersecurity office within the Executive Office of the President, so part of the White House. And this happened, but actually even before that, there were a couple of interesting things. So the government asked for input on open source software security. This was a request for input from CISA, which is the Cybersecurity and Infrastructure Security Agency, the Office of the National Cyber Director, the National Science Foundation, DARPA, which is the Defense Advanced Research Projects Agency, and OMB, the Office of Management and Budget. I'm trying to just give, there's a lot of acronyms, I'm trying to give them all. But this is basically asking industry and academia for input on how to achieve better security in open source software. And a bunch of companies responded and recommended moving to memory safe languages. So I listed a few of them here: Microsoft, Google, Cloudflare, GitHub, IBM. I'm listing GitHub separately. They are owned by Microsoft, but they operate as an independent company. So I'm listing both. They sent separate responses. So all this is to say that these are companies basically saying that even without the presence of regulation to force them to move to memory safety, they want to move to it anyway. And when you read them, sort of they're writing about it, what they say is it saves them money. It makes operations easier. It makes things so like debugging memory safety issues or trying to like enforce security on C and C++ code bases is difficult, and moving to a memory safe language is easier. Google, for example, on the Chrome and Android teams have instituted what they call the rule of two, which is basically that new code either has to be sandboxed or it has to be in a memory safe language. Sandboxing is really hard. Like doing it correctly and successfully sandboxing stuff is hard. So mostly new code ends up being in memory safe languages because people don't want to do all of the sandboxing the new stuff they're writing. So companies are choosing this stuff because it's valuable to them, even separately from there being any like regulation, which at least in the US and in the EU, there isn't today. So the move to memory safe languages is happening, but what does this mean for the state of vulnerabilities? So I mentioned CWE before. Every year they put out a top 25 list. This basically is where they look at data for the last year of CVEs. This is publicly disclosed vulnerabilities that have had a CWE mapping. So someone has determined what weakness applied to that vulnerability, and they figure out what were the most common ones in the last year. In 2024, 20% of the top 25 were memory safety related, and 35% of the known exploited are memory safety related, because there's also a separate list called the known exploited vulnerability list, or KEV list. They catalog the numbers there. So this is to say that it's 20% of the top 25, but it's 35% of the known exploited. These are real vulnerabilities that are getting exploited in the wild and they're memory safety related. Now, we're always going to have bad authentication authorization handling, bad neutralization of user input, resource exhaustion. If you look at that list previously, a bunch of those are of those types. Like someone accessed a thing that they weren't supposed to, or they caused the computer to run out of resources and it fell down, but like we're not really going to be able to get rid of those at the programming language level. But there is still a really interesting question of if memory safety vulnerabilities become much less common because we've basically developed a common technique through memory safe languages for addressing them, what other kinds of things should rise to the fore or might be interesting if you were a person who was previously engaged or interested in low-level exploitation? What other things might you look at if that becomes less common or less viable as that software sort of just lowers in prevalence? So I'm going to run through some different things. Now, these are going to be overviews. If any of these interest you, I encourage you to research them, read into them. Feel free to reach out to me. I'll have my contact info at the end. I'm happy to talk about them. So the first thing is micro-architectural vulnerabilities. Anyone remember Spectre and Meltdown? Okay, couple. So Spectre and Meltdown and the other things that are sort of around them, these were the first category of that were modern like microarchitectural vulnerabilities. They really created this new class that since then there have been a bunch more. This is basically where the modern computer architectures, for reasons of performance, like to do things with prediction. They like to do things like, anyone here ever heard of a branch predictor? Awesome. So a branch predictor basically says, I noticed that there's a conditional in this program that I'm running, and I really want to guess which path that conditional is going to take. I'm going to speculatively execute some stuff based on the assumption that I'm correct about that branch. If I'm wrong, I'm going to have to roll back some stuff and right, then I basically get performance benefits because by the time the program gets there, like I've already done the work. It's a way of improving the performance of programs at the architectural level. It turns out you can trick these things constantly, and it turns out CPUs have tons of predictors, and you can basically trick them and use that to get around things like access controls in ways that are really, really troubling. So Spectre was basically tricking the branch predictor into leaking data, where if you sort of took a branch one way a bunch of times, you could then take it the other way and use sort of fact the branch predictor is going to be wrong to access data that you shouldn't be allowed to access, because on the other path, you would basically try to access stuff that you don't actually have at the hardware level the right to access, but because it's speculatively executing, the hardware wouldn't check. And then you could use a side channel to get data out. meltdown was similar. You could basically read memory faster than the privilege check happens and get the result of the read before the privilege check comes back saying, hey, you're not allowed to read that. There's a bunch more, but these were like the first two. They affected every Intel processor made from 1995 to 2018. And this is not Intel specific, so like these are just names of other things in this kind of style, and a bunch of these are actually underneath multiple vulnerabilities themselves. So you have this whole world of like targeting the microarchitecture to find different predictors that you can trick and use to bypass controls. And this is still happening, and it's not just Intel. This is from this year. There were some new vulnerabilities in this class against Apple M2 A15 chips. These are reasonably recent Apple chips for iPhones with the A15 and for MacBooks and Mac devices with the A2. A mode address predictor, a mode value predictor. You can trick both of those and use that to access things that you shouldn't be allowed to. So these keep happening, and there is this open problem of how can we have fast processors that aren't full of these vulnerabilities? These keep happening. So it's still a very active space and a really interesting one. Next one, cryptographic vulnerabilities. So cryptography libraries are better than they used to be. When Heartbleed happened, OpenSSL, like people started to pay attention to how was OpenSSL developed. It's like 3 people part-time. None of them were really being paid for the work. And this is for an extremely popular open source software library that we use all over the place. I mean, it is probably the most widely used implementation of SSL TLS, which basically secures everyone's web traffic. And so after Heartbleed, OpenSSL did get investment and support, and they've made a number of improvements. There were also a couple of security-related forks. There was LibreSSL, and then there was Boring SSL, which both tried to kind of improve the security state. And just more generally, there's been improvement in the design of cryptography libraries. In the security engineering world, or cryptography engineering world, there's been this idea of like misuse-resistant API design. So it's kind of like, can you design cryptography libraries where the design of the API helps you to not do the wrong thing? Because cryptography, if you think of each little like cryptography primitive that you have and you're stitching them together to make a protocol, if you stitch them together in the wrong way, the whole thing doesn't work. Like it is very sensitive to getting those pieces right. And so, how can we build libraries to make that happen? And there's just also generally been improvements in primitives. We've gotten better at creating just like the sort of baseline materials that you would use to put together a cryptography protocol. We have better understanding of things like authenticated data, just kind of like how to do correct protocol construction. So the world of cryptography overall has matured a lot. It's quite good, but primitives being correct doesn't mean a protocol is secure. So this article, this is from a cryptography researcher named Soatok, or goes by the handle Soatok. Hell is overconfident developers writing encryption code. And this is basically him looking at, there was a startup which had written some blog posts about their custom protocol that they've made for sharing secret materials within the company that was completely broken. And in fact, the class of vulnerability, or like the sort of mistake that they made, is one that has been known to cryptography engineers since, I think it was 1990. But because the people making it were sort of assuming, like, I don't know, I'm putting together cryptography pieces that all seem like they work together, and I'm just gonna, like, I'm a good developer, I'll put them together, unintentionally made a mistake that had been known for 25 years. So just because the primitives are good doesn't mean the protocols are. There's also, anyone here looked into quantum computing and its impact on cryptography? Generally, we're gonna group the cryptography that we use today into 2 groups. There's the finite field cryptography, and there's elliptic curve. Both of those are broken by quantum computers. And it's entirely possible for attackers to harvest data now and wait for the development of a quantum computer that is good enough to decrypt it. This is the harvest now, decrypt later problem. So we need post-quantum cryptography. Many existing protocols can't easily adapt. Like TLS, it has a huge amount of key material, and the key material needed for post-quantum cryptography is a lot bigger than the key material needed for our cryptography we use today. There's not a clear answer on how to fit it into TLS yet. So yikes. Supply chain vulnerabilities. This is actually a lot of what I do. Code reuse is good. It is good when people use open source software and they avoid having to redevelop things themselves. But anyone here hear about the XZ-utils attack last year? So this attack, there's a really detailed timeline that you can go look at. I mean, just I'll go to the next slide. Seriously, go read the story of this attack. Russ Cox, who's one of the developers of the Go programming language, did a really, but basically a malicious attacker socially engineered their way into becoming a maintainer of a popular, widely used open source library, and then executed an extremely technically sophisticated supply chain attack to specifically subvert and provide remote code execution on a small number of Linux distros that package this particular library in a particular way. Very, very sophisticated, really targeted, and it was found by accident by a PostgreSQL developer who noticed a slight performance drop on a test version that he was working on. And if he'd found it even a few weeks later, this would have been global and the impact would have been extremely severe. Like we got very lucky with XC utils. But also we have things like more common stuff, typo squatting, malicious contributions made to open source projects, account takeovers, token reuse. There's a lot of work now on trying to secure the infrastructure that's used for software supply chain stuff. So conclusions, memory safety vulns are not going to disappear. There's still lots of existing code written in memory unsafe languages. We should still expect that buffer overflows and use after free, things like that are going to exist. But I do expect that as there's more of a move toward memory safety, that those will become less common. And so there's lots of interesting opportunities to say, well, if those aren't going to be the bread and butter of someone who's looking for CVEs, what other kinds of interesting things are there beyond the usual authentication issues or other kinds of like system level stuff that's never going away. So basically, there's still a lot to secure, and I really highly encourage everyone to be curious. So thank you, and
Does anyone have any questions for Andrew?
right. So just for the benefit of people online as well, the question is basically about whether smaller companies will have trouble with adopting memory safe languages. I will say for that, I expect there's going to be a long tail of companies which are slow to adopt this, and it's going to also depend on certain industries. Changing languages is a big deal and often includes challenges around like the availability of libraries that you may depend on. I also think not everything is necessarily going to be rewritten. It might be that new code transitions to memory safe languages, or that you have safe interfaces for existing unsafe code that tries to enforce safety. There are different routes to deal with that, but I do think there's going to be a long tail of companies that are slow to make this transition. This is kind of like a decades scale transition and not like a next few years. So the question is about whether you should learn memory safe languages or memory unsafe languages first. I think learning with a memory safe language first is useful if you're just trying to understand, like you're learning programming for the first time and you want to focus on just kind of like how programming works. That said, I do think that it's useful to learn how the computer actually works, like to learn the details of your architecture, to learn the details of application. This is not to say, people will sometimes say that like, oh, with C, you're programming the hardware. No, you're not. You're programming the C virtual machine, which may or may not match your actual hardware. But I do think that the facilities available in memory unsafe languages give you extra power and can be a useful educational tool. But I think that that's secondary to just learning the fundamentals of how do programs work and like what is programming. So I would say second. Right. So the question is, how do you get used to Rust syntax? And I mean, honestly, the answer is just to do it. So I picked up Rust 11 years ago when I was still in undergrad. I was in a largely C++ focused degree program, and I did not like C++ very much. And so I was very happy for something which was usable in the same context, but offered memory safety. But also I've been writing Rust for so long that it's very comfortable for me at this point. But yeah, I think just doing it, and if you can find opportunities to be mentored or to take classes, things where you're going to get sort of support and have opportunity to ask questions, clarify confusion. I think that that tends to be a better route. I'll also say with Rust, I highly recommend reading the book and really going through the sort of standard track of how to learn the language rather than trying to take an existing program written in C and rewrite it in Rust. A lot of the idioms that are common in C, Rust will refuse to compile because it can't prove that they're safe, and you often end up asking for a world of hurt trying to just translate one into the other. It's not a very fun way to try to learn Rust. Right, so the question is basically whether memory safety issues intersect with the memory protections that operating systems offer. And I mean, basically today for any major operating system, you can generally expect their memory protections pretty much work. They are well tested, even though these operating systems are usually written in memory unsafe languages, they've been assured over a long period of time and investment, so you can feel confident in them. That said, there are possibilities that memory safety protections provided by operating systems in them that are only possible because of the fact that they're written in memory unsafe languages. There's a long sort of debate about whether it's possible to write operating systems that are competitors to ones available today that are written in memory safe languages. I generally think that it is, but it's its own sort of challenge, and the things that exist today are small scale. The Oxide Computer Company, for example, has a small operating system. It's a microkernel called Hubris, which is written entirely in Rust. It's great. It's open source. It's on GitHub. I highly encourage looking into it. But the world of memory safe languages for operating systems is still relatively small. This question is about one thing hurting Rust's adoption is async programming. Basically, someone saying that they don't feel that Rust handles asynchronous programming very well. So I would say that I think that's wrong. I think that Rust async programming, as someone who does it professionally, I think it's great. That said, I think that there are still rough edges around the use of it, places where libraries are still kind of challenging or need to be addressed. There are some historical reasons for the Rust project that people who were involved in the development of async early on sort of dropped out after the initial stuff landed, and so there's kind of a usability gap. But the semantics, the guarantees you get from it, and the performance are all fantastic. So I know that there's a new version of the Rust async programming book, which is underway, being written by Chris Krycho and a couple of others, who I really trust to write good materials. And I know that there is renewed interest and work on improving the state of the Rust sort of async library ecosystem. So I think that it's good, and generally, yeah, I don't buy into like people just hating on async programming. That's actually not true. There are ways to do it with safe code. I can talk with you afterward about how to do that correctly. But so the question is sort of like web programming in Rust and kind of challenges around doing multi-threading. You heard mention of Arc and mutex. So this is basically where Rust, its central constraint is what's called aliasing exclusive or mutability. Data can either be aliased, meaning it's accessed by multiple places, or it's mutable. You can't have both. There are types in Rust which relax these constraints, and you sort of compose them together to get the exact constraints that you need. So in your case, for example, if you want to have a single piece of shared state, which is accessible across multiple threads, you can put it in thread local storage. You can have multiple reference counted pointers from different threads to access the data, mutex type to manage mutual exclusion so that there's never shared mutability. But you're composing these separate pieces, and syntactically it can seem heavy. The trade-off is that you have a lot of power over exactly what constraints you want to place over data, and you never lose Rust's guarantees around aliasing XOR mutability, which is central to its correctness guarantee. So it seems heavyweight, but the benefits are substantial, and I do think it's necessary. Yeah, Rust does sort of make certain pieces of complexity kind of your problem that are hidden by the language runtime in languages like Java. There are trade-offs for doing that. And it, like, as much as I love Rust, it's not the only memory safe language, and it's not always the best choice. So I think I'm at a pass.